$900,000. Not for a startup founder, not for a hedge fund manager, not even for a star athlete, for an engineer. And not in California, in Beijing. Somewhere inside China's semiconductor ecosystem, certain specialists were reportedly being offered compensation packages approaching $900,000 a year to join a single research program. That figure sounds irrational until you realize what was at stake. If a handful of engineers could shave even 12 months off China's dependence on foreign chip technology, the return on investment wouldn't be measured in salaries. It would be measured in national power. Because advanced semiconductors aren't simply products anymore, they're leverage. The smartphone in your pocket, the servers training artificial intelligence models, modern fighter jets, medical scanners, autonomous vehicles, industrial robots, none of them function without increasingly sophisticated chips. Whoever controls the ability to design and manufacture them gains influence over entire industries. Washington understood that years ago. That's why in October 2022, the United States introduced sweeping export controls aimed at limiting China's access to cutting-edge semiconductor tools. The restrictions targeted equipment produced by companies such as ASML, Applied Materials, and Lam Research. American citizens working in certain Chinese chip projects were suddenly forced to choose between their jobs and their passports. The expectation was fairly straightforward: slow China's progress, buy time for American companies, maintain a technological lead. On paper, it was a logical strategy. In practice, something unexpected happened. China didn't stop. It accelerated. Funding expanded through the National Integrated Circuit Industry Investment Fund, often called the Big Fund. Provincial governments launched their own semiconductor initiatives. Universities increased enrollment in microelectronics programs. Research institutes began recruiting aggressively, sometimes offering compensation packages that looked more appropriate for investment bankers. Apparently, sanctions have a strange side effect. They occasionally convince people to spend even more money. But the salaries weren't the most interesting part. Money alone doesn't create expertise. A nation can purchase machines. It can purchase buildings. It can even purchase patents. Experience is harder. A process engineer who spent 15 years solving manufacturing problems at a leading foundry carries something far more valuable than a diploma. They possess accumulated failure, thousands of tiny mistakes, hundreds of adjustments, dozens of production crises that never appeared in academic journals. That knowledge cannot be downloaded. It has to be lived. And Beijing seems to have reached a conclusion that many policymakers elsewhere underestimated. If catching up traditionally takes 20 years, perhaps paying extraordinary amounts to attract and concentrate specialists can compress that timeline dramatically. There's precedent for this kind of thinking. During the late 20th century, countries such as Japan and South Korea imported expertise from abroad, studied foreign manufacturing methods obsessively, and eventually built globally competitive industries. The difference is scale. China isn't trying to dominate televisions, it's trying to master the most complex manufacturing process humanity has ever commercialized. Producing advanced chips means controlling structures measured in nanometers, dimensions so small that a human hair appears gigantic by comparison. One contamination particle can ruin an entire wafer worth hundreds of thousands of dollars. And despite those difficulties, reports began emerging that Chinese laboratories and firms were making progress on technologies many analysts believed would remain out of reach. That raises an uncomfortable question. What if the export controls succeeded in limiting access to foreign tools, but unintentionally encouraged China to become more self-reliant? I wasn't entirely convinced at first. There are strong arguments against that idea. China still depends heavily on imported lithography equipment. American companies remain dominant in electronic design automation software. Dutch and Japanese firms retain advantages in critical components. These are serious obstacles. Yet obstacles and barriers aren't always the same thing. History is full of examples where determined states treated technological isolation as an engineering problem rather than a political defeat. And then something happened inside one laboratory, reportedly built around a small cluster of highly paid engineers, that caused officials in Washington to pay much closer attention, because the chip that emerged wasn't supposed to exist, at least not yet. And understanding how it appeared requires looking at a company most people outside the semiconductor industry had barely heard about a decade ago. Its story starts long before those $900,000 salaries ever appeared. By 2014, almost nobody outside China paid much attention to a company called SMIC. Investors talked about Taiwan Semiconductor Manufacturing Company. Engineers admired Intel Corporation. Governments worried about Samsung Electronics. SMIC was usually mentioned as an afterthought. Its manufacturing technology lagged behind industry leaders by several generations. Yield rates were inconsistent. Advanced process development moved slowly. If someone had predicted that within a decade, SMIC would be producing chips approaching 7-nanometer class performance under some of the harshest sanctions ever imposed on a technology sector, most analysts would have dismissed the idea. Not because Chinese engineers lacked talent, because semiconductor manufacturing is brutally cumulative. Imagine trying to become a chess grandmaster, except every move costs millions of dollars, the rulebook changes every few years, and your opponents refuse to sell you half the pieces. That's semiconductor fabrication. The company spent years hiring specialists from Taiwan, South Korea, Europe, and the United States. Some came for better compensation. Others came because they saw an opportunity to build something from scratch. A few returned simply because they believed China's market would eventually become too large to ignore. Remember the point from earlier. China wasn't only purchasing knowledge, it was purchasing time. A veteran process engineer doesn't just understand how to manufacture a transistor. They know why previous attempts failed. They remember which chemical mixtures increase defect density. They recognize subtle patterns inside production data that younger engineers might overlook. That experience compounds. And Beijing understood compounding. By 2019, China was spending billions annually on semiconductor research programs. Universities such as Tsinghua and Fudan expanded chip-related departments. Regional governments in Shanghai, Shenzhen, and Wuhan competed aggressively to attract talent. The salaries became headlines. The ecosystem mattered more, because an engineer earning $900,000 still accomplishes very little if suppliers, universities, testing facilities, design houses, and equipment manufacturers don't exist nearby. China spent years trying to ensure they did. Then, Washington tightened restrictions again. The United States persuaded allies to limit exports of extreme ultraviolet lithography systems produced by ASML. These machines are among the most complicated devices humans have ever assembled. Each costs more than $200 million. They contain hundreds of thousands of components and rely on lasers powerful enough to vaporize droplets of tin 50,000 times every second. China couldn't buy them. That should have ended the story. Except SMIC appears to have chosen a different path. Instead of waiting for access to EUV machines, engineers reportedly pushed older, deep ultraviolet equipment beyond what many experts considered practical. It wasn't elegant. It wasn't efficient. It probably wasn't cheap. But engineering isn't always elegant. Sometimes engineering is simply refusing to accept the default answer. And in 2023, researchers analyzing processors manufactured for Huawei's Mate 60 Pro smartphone reached a surprising conclusion. The chip appeared to have been fabricated using a process comparable to 7 nanometers. People immediately started arguing. Some analysts suggested inventories of older tools had been stockpiled before sanctions. Others proposed that yields might be too low for mass production. Both explanations may contain some truth, yet they also miss something important. A country doesn't need perfect efficiency to challenge assumptions. It only needs to demonstrate capability. That was the real shock. For years, discussions about China's semiconductor future revolved around timelines. 5 years behind, 10 years behind, 15 years behind. Suddenly, the conversation changed. How far behind was China actually? No one seemed completely certain anymore. And uncertainty is uncomfortable in geopolitics. Governments can plan around known weaknesses, They struggle when those weaknesses begin shrinking faster than expected. I think that's why the laboratory mentioned earlier attracted attention. Because producing one chip isn't necessarily impressive. Anyone with enough resources can build prototypes. Building a repeatable process is different. Building an institution that teaches younger engineers how to improve that process is even harder. That's where those extraordinary salaries start making sense. Beijing may not have been paying nearly $1 million per engineer to create a single breakthrough. It may have been paying them to become teachers. To transfer decades of accumulated manufacturing intuition into an entirely new generation. If that's true, then the most valuable product emerging from these laboratories isn't a chip, it's people. And ironically, that creates a problem sanctions alone cannot solve. Because once knowledge spreads through thousands of engineers, recalling it becomes impossible. A machine can be denied export licenses, experience cannot. And this is where the story becomes more complicated than either Washington or Beijing would probably like to admit. There's a temptation to tell this story as if one side is winning and the other side is losing. Reality is messier. China has made undeniable progress, but it still faces constraints that don't disappear simply because a laboratory produced an impressive chip. The semiconductor industry isn't one industry. It's dozens of industries stacked on top of each other. Materials, chemicals, software, metrology systems, packaging, inspection equipment, specialized gases, precision optics. Miss just one layer and the entire chain starts wobbling. Even today, Chinese companies remain dependent on foreign suppliers in several critical areas. Electronic design automation software is still dominated by firms such as Cadence Design Systems, Synopsys, and Siemens EDA. Japan continues to hold significant advantages in photoresists and advanced semiconductor materials. ASML still possesses capabilities that nobody else can replicate at scale. These aren't small details. They're structural advantages built over decades. And this is where I have to challenge my own argument. Maybe Washington's strategy is actually working. After all, Chinese firms are spending enormous sums just to recreate technologies already available elsewhere. Some estimates suggest domestic alternatives can cost substantially more and operate with lower yields. A process that produces 95 usable chips out of 100 wafers is economically very different from a process producing 70. Margins matter, investors care, manufacturers definitely care. If sanctions force China into a slower, more expensive path, perhaps the objective has been achieved. That's a reasonable position, but I think it overlooks something deeper. Countries don't always optimize for efficiency. Sometimes they optimize for resilience. Think back to energy policy. Europe spent years purchasing inexpensive Russian natural gas because it was economically rational. Then geopolitics intervened, and suddenly governments became willing to pay much higher prices for alternative supplies. The logic changed. Security replaced efficiency. China appears to be applying that same principle to semiconductors. The question isn't, can we manufacture chips more cheaply than Taiwan? The question is, can we manufacture enough advanced chips ourselves if foreign supplies disappear tomorrow? Those are completely different objectives. And once viewed through that lens, some seemingly irrational decisions begin making sense. Consider Huawei. Before sanctions, the company relied heavily on foreign suppliers and international manufacturing partners. Losing access to them was supposed to weaken its long-term competitiveness. Instead, Huawei redirected resources into internal research, software development, and domestic supply chains. The company reportedly invested more than $23 billion in research and development during 2023 alone. That's larger than the annual GDP of some countries. One company, 1 year. And here's the reversal. The chip emerging from that highly funded laboratory may not even be the most important outcome. Remember the engineers earning extraordinary salaries? Imagine a team of 20 veterans mentoring hundreds of younger specialists over 5 years. Those younger engineers train thousands more. Knowledge spreads. Mistakes become case studies. Production problems become classroom material. Eventually, an ecosystem develops institutional memory. At that point, progress becomes difficult to stop. Not because breakthroughs happen every month, Because setbacks stop being fatal. The Soviet Union built rockets while isolated from much of the Western industrial world. Japan rebuilt its manufacturing sector after devastating wartime destruction. South Korea transformed itself from an importer of consumer electronics into a country producing some of the world's most advanced memory chips. History suggests that technological gaps are rarely permanent, especially when a country has money, talent, and political commitment aligned toward a single objective. Still, there are limits. China's semiconductor ambitions aren't guaranteed to succeed. Corruption scandals have affected parts of the Big Fund initiative. Several domestic projects collapsed after receiving billions in financing. Building a semiconductor ecosystem isn't like constructing highways. You can't simply pour concrete faster. Some lessons require years. Some failures require decades. And that's what keeps policymakers awake at night. No one truly knows whether China's current trajectory leads to self-sufficiency by 2030, 2035, or perhaps never. What we do know is that the assumptions many people held in 2022 look less certain today. The expectation was stagnation. Instead, the picture resembles adaptation. And adaptation has a habit of changing strategic calculations, especially when artificial intelligence is beginning to consume advanced chips faster than manufacturers can produce them. By the end of this decade, that demand may matter even more than who reached 7 nanometers first. Because the real competition might not be over technology. It might be over who can sustain technological momentum the longest. Let's go back to the number that opened this video. $900,000. At first glance, it feels absurd. A government or a company paying nearly $1 million a year for an engineer sounds like panic disguised as strategy. After looking deeper, I'm not sure that's what we're seeing. I think Beijing reached a conclusion years ago that many countries only recently began accepting. The 21st century won't be defined primarily by oil reserves, aircraft carriers, or even access to rare minerals. It will be defined by manufacturing competence, not factories, competence. The ability to take an idea from a laboratory notebook, transform it into a prototype, improve it through thousands of iterations, and eventually produce millions of units with acceptable yields. That capability can't be switched on during a crisis. It has to exist beforehand. That's why I suspect those highly paid engineers were never expected to justify their salaries through a single breakthrough. Their mission was probably much broader. Build teams, train successors, create processes, develop habits, teach younger researchers how to solve problems nobody has written textbooks for yet. Because once an ecosystem learns how to learn, catching up becomes easier. And that realization matters far beyond semiconductors. Artificial intelligence training clusters require advanced processors. Military systems increasingly depend on sophisticated computing hardware. Quantum research demands specialized fabrication techniques. Future medical devices will rely on sensors and processors that haven't even been designed yet. The country that controls enough chip production capacity doesn't merely sell products, it gains options. During periods of geopolitical stability, options are nice to have. During periods of tension, they're priceless. Washington understands this. Beijing understands this. Taipei understands this. Everyone involved understands this. Which explains why the semiconductor industry increasingly resembles an insurance policy rather than a business sector. Insurance policies are expensive. People complain about paying for them until the day they need them. That doesn't mean China has already won. Far from it. The United States still possesses extraordinary advantages. American universities remain magnets for scientific talent. Companies such as NVIDIA, AMD, Apple, Broadcom, and Qualcomm continue setting the pace in chip design. The United States also retains powerful alliances with Japan, South Korea, the Netherlands, and Taiwan. Those relationships matter, a lot. But I think policymakers in Washington may eventually discover that sanctions work best when the target lacks scale. China has scale. China has engineers. China has capital. Most importantly, China appears willing to tolerate inefficiencies that private investors would reject immediately. Governments play different games. They can afford to think in decades. Markets usually think in quarters. My prediction is fairly simple. By 2030, China probably won't dominate the most advanced semiconductor technologies. I don't think it needs to. If Chinese manufacturers can reliably produce enough chips at 7 nanometers, 5 nanometers, or even slightly older nodes to satisfy most domestic demand, the strategic picture changes significantly. The objective was never necessarily to surpass everyone. The objective may have been to ensure that no foreign government can halt Chinese technological development with the stroke of a pen. And if that's the goal, paying $900,000 for a world-class engineer suddenly feels less like extravagance and more like a rounding error. I'm still not completely certain that Beijing's approach succeeds. Semiconductors have humbled brilliant people for decades. Physics doesn't negotiate. Yield rates don't care about political speeches. Contamination particles certainly don't read government directives. But I am convinced of one thing. The assumption that export controls alone would freeze China's semiconductor ambitions belongs to an earlier chapter. We're reading a different chapter now. Maybe the laboratory mentioned at the beginning truly produced a chip Washington cannot currently match under the same constraints. Maybe it didn't. In some ways, that's no longer the most important question. The more important question is whether a generation of Chinese engineers has already learned enough that the next laboratory won't need to pay anyone $900,000 at all. Because if knowledge has started compounding inside China's semiconductor ecosystem, then the most expensive part of catching up may already be over. And history has an odd habit. It rarely announces when a technological race changes direction. People usually notice years later. Then they write reports explaining why they should have seen it coming. If you enjoyed this analysis, stick around for the next one. The semiconductor story is still being written, and frankly, the engineers seem determined to keep giving policymakers fresh headaches.